All right, and this installment of biochemistry is carbohydrates. Carbohydrates just a fancy name for sugar. The most common sugar that we're going to deal with in intro chem is glucose. It's the one that's the easiest to make polymers from. So when we think of a lot of our starches and celluloses and so forth, it's all glucose based. So when in doubt in the homework, if you see glucose, it probably is the answer. What's unique about sugars is their ability to repeat themselves into polymers. So in this case, the sugar monomer is typically, again, glucose. When they come together, they're using their alcohols to make what looks like an ether. So if you can imagine that the sugars are R groups, that they're random groups. This is random O random. It's got a sugar on ether side, so ether or either kind of sounds the same in that kind of sense. So just be aware that we call them ethers by organic chemistry, but in biochemistry they name these ethers based on their biological name, and that's the glycoside linkage. Just like proteins have a mid linkage, we call them peptides, so no peptides for the test. Here we need to know that glycosides are the sugar linkage, and that's what we need to know rather than the actual ether structural name that we would call it in a previous chapter. If you have parents or grandparents that have issues with sugar, they might have hyper or hypoglycemia. You can imagine that that's where this glycoside kind of linkage name comes from. Much like we mentioned with proteins, you get those from a lot of meaty and protein-rich foods. Carbohydrates are a little bit different. They're hydrates of carbon, meaning its reducible formula is CH2O, H2O being water. This is a carbo, so carbon, hydrate, which is water. So we get that name. It also ends in OSE. We have to be careful with that because enzymes in our previous section end in ASE, and those enzymes are protein-based, not carbohydrate-based. So a lot of our breads and pastas, a lot of our fruits and vegetables, and a lot of our processed sugars where we're going to find these molecules, and mostly these molecules provide us with energy. So our simplest energy that we can get the fastest from our body is by breaking down these, carbon sugar-based units. So monosaccharides are simple sugars. Monosaccharides tend to have aldehydes and ketones. This is what gives them their aldose and ketose kinds of names. This is also where you hear of the keto diet or the, somebody's blood that's in ketosis or something like that. It's all based on sugar-related ideas. We can also take sugars and ferment them into drinking alcohol, and you can imagine that the reason we can do this is because sugars themselves have so many alcohols already. Just about every carbon on the chain has an alcohol, and if it doesn't have an alcohol, it typically has an aldehyde or a ketone instead. If you have 6 carbons, you're considered a hexose sugar. If you're 5 carbons, a pentose sugar. So you can see those prefixes showing their face again. But what's most important is different from proteins that have amines and acids, carbohydrates are very different. They have aldehydes and ketones and lots of alcohols that make them super water-loving, super polar. Because you can imagine that alcohols are ROH, water is HOH, and they have a lot in common. Specifically their polarity and their shape. Disaccharides are when you put 2 sugars together. So remember, sugars and saccharides both start with S, and proteins and peptides both start with P. That can help you make that distinction on the homework and the exam later on. Sucrose is the most common sugar that you probably deal with, and that's in table sugar. It's what happens when you take glucose and fructose together. Our body can deal with glucose a little bit easier than fructose. Some studies even say that fructose can actually cause things like cancer. There's plenty of other studies that say that that's not the case, but it's kind of contested the purpose and the usefulness of fructose because really your body wants glucose units, and fructose is just kind of the byproduct of our table sugar. Pretty unique to both proteins and carbohydrates is they're both condensation polymers. So if you join carbohydrates together to make water and produce water, and water leaves, that's no different than what happened with 2 amino acids when they joined together to make water and water left. And we mentioned that with, say, surgeries, when you cut your skin, that water is produced. So when you form carbohydrates into longer chains, they produce water as well. So you can imagine for both of these, if we want to break apart a sugar, if we want to break apart a protein when they produce water in their production, the only way to reverse that process is to allow water back in. So all dietitians are going to tell you to drink plenty of water, and this is exactly why. If you want to break a glycoside linkage in, if you want to tear it into two pieces, what needs to happen is you need water, H2O, to come back in so that it can break this into two pieces. So notice there was an oxygen there. Here we have H2O. So we need water in order to separate a disaccharide into its monosaccharides, or same thing for a polysaccharide. If it's a long chain of glucose monomers, then we need lots of water in order to break those apart. And that's no different for proteins. Proteins also need water in order to be digested with the help of their enzymes. Polysaccharides are even worse. So the problem with polysaccharides is they're long chains of typically glucose. And a good example of this would be cellulose or starch. A lot of cellulose and starch fibers that we eat are held intact the entire time. If our body was designed to eat plants only, then we'd have multiple stomachs like cows that are designed to eat plants only. Because the reality of the structures in all those plants is they are, very well held together. That's why they resist the rain and the sun and the storms and the snow and so forth. Trees are strong for a reason. That's because these starch and cellulose fibers that make up them have a tremendous amount of glycoside linkages that have to be broken apart. But also they lay together in very strong layers, just like nylon did. But in this case, much stronger because now we're using OHs instead of NHs. So in order to digest a cell wall plant kind of structure, we're going to have to break the hydrogen bonding. And when there's millions, trillions of these glucose polymers, and there's millions, trillions of these glucose strands of polymers, that's a lot of hydrogen bonding to break. Once we break strand from strand, then we have to go through and break hydrogen bonding between the strands themselves. Break it between the, strands themselves. And then finally, we have to go in and use the help of, say, enzymes to break those glycoside linkages. And all of that needs to happen in, a day or two, because then it comes out the other end. So the reality is, most of the time it doesn't. So when you eat corn, it still looks like corn on the other end. And that's the reality of structure and polarity. In this case, it's too polar, too well glued together, that we can't break apart those starches before they're too late. So oftentimes, a lot of the reasons that people eat a lot of lettuce-based, food items is because it makes your stomach feel full, which is a good thing because then it doesn't have room for another piece of cake, which would give you more energy than you're going to probably consume in the next day or two, and that's when you start gaining weight. So a lot of starches and, plant-based materials are good for your diet because they give you some fiber to get things moving along. But other than that, they're not too useful because our body isn't like a cow's where it has multiple stomachs to digest. We also don't have the ability like cows to throw up our food and then chew it again to add more enzymes to it so that it can help in the digestive process. So again, that's why, we're meat and plant eaters, because our body is designed that way based on its enzymes. And then we talk about lipids in a separate chapter. So much like carbohydrates, lipids are energy, but these are typically long-term energy. So once our sugar-based energy is depleted in our bloodstream, then our body starts to go after our lipids because that's the only thing left. So we'll talk about those in a separate section, but those are another type of energy molecule coming up.